In this session, we'll talk about the last topic of this chapter, which is vertical motion. So it is basically vertical circular motion. So let me call it a vertical circle. So we'll basically find out the necessary condition for a particle to be able to complete a vertical circle. Now we have dealt with a similar situation before. If you remember, we'd seen that if you have a pendulum of length L and mass m, then we had analyzed the oscillation of this pendulum if it is slightly disturbed, right? So this time we'll talk about a situation where this bob, while at its lowermost position, is given some initial velocity, let's say V0, and then we'll see how with the variation in V0, this pendulum will exhibit different kind of motion, right? So first of all, let's draw our axis. So let this be the x-axis. So this point, this axis passes through the point of suspension, and along the length we have the y-axis. So now, when we draw these axes, we can talk about quadrants, right? This is the first, the second, the third, and the fourth quadrant. So if the velocity given is not very large, then you know this pendulum will only start to oscillate, right? It will first move towards the fourth quadrant and then keep moving back and forth. Now, we have analyzed the situation, so let's just briefly do it again. If the pendulum is moving such that its displacement, so let me draw it in a displaced position. So this is a position in which it is slightly displaced. So let's say if this displacement is theta, then first of all, I'm talking about a case where theta is less than 90 degrees, right? So this pendulum is not oscillating with the maximum displacement more than 90 degrees. So if that is the case, the oscillations are restricted to the third and the fourth quadrant, right? So in such a case, during motion, if we talk of a general point, you would see there's a tension that acts along the length. Then there is weight of this bob, mg, acting downwards. And if we are viewing this from an inertial frame, then these are the only two forces which are acting on the bob, right? Then we had seen that to analyze this situation, we had broken down mg into components, one parallel to the length, other perpendicular to the length, right? So if the displacement with respect to the vertical direction is theta, then this angle is also theta. So you could break mg down into mg cos theta, which is along the length, and mg sin theta, which is perpendicular to the length. Now, in this case, always be careful. What you can certainly see is that there will be no motion in the radial direction, right? The bob will never move towards the center. So you could have a tendency to balance tension with mg cos theta. Now, this is a very common mistake that is often made. But the problem is that even though this particle never moves in a radial direction, it is going in a circular motion. And we know that whenever a particle moves in a circular motion, it has a constant acceleration directed towards the center, and its magnitude is v square by r, right? So for these oscillations, for small oscillations, that is theta is less than 90, the particle always stays below, and the equations look something like this, that t minus mg cos theta provides the required centripetal, which is mv square by r. The r in this case is equal to the length of this pendulum, right? The second equation, if you wish to write, is that mg sin theta, the second component of the force, is equal to mass into acceleration, right? Because it is a single force, so this force is equal to mass into acceleration, right? in this equation, what you see is that we are basically going to focus on tension, and it will become clear why as we go on. So the tension here you see is equal to mg cos theta plus mv square by L. So this is the expression for tension for the oscillations in the third and the fourth quadrant. That is, the pendulum is not yet displaced for an angular displacement greater than 90. Right. So now if you look at each of these terms, this term mv square by L is a positive quantity. Right. Also, mg cos theta, if theta is less than 90, this will always be a positive quantity. Right. And in fact, this term, this first term mg cos theta, this can never be 0, right? Because cos theta can be 0 only if theta is 90. And we are talking about angles which are less than 90 degrees, right? So this tells us that for small oscillations, tension can never be 0, right? This tells us that tension is always greater than 0. So this is the key idea here, that for small oscillations, we can certainly say that tension will always be greater than 0. Now, the reason we are talking about tension is that if the tension becomes 0, what do you think will happen to the string? Well, one result could be that the string begins to slack, right? Because if it's not held tight, it can have a tendency to slack. So if tension is greater than 0, we know that string will never start to slack, right? Now, this is the case when theta is less than 90. Now, first of all, let's find out the maximum value of speed with which we can throw this bob such that the speed is always, the angular displacement is still less than 90. Right. To find that, we will look at a critical case where the velocity given, this v0, is such that theta just manages to reach 90 degrees, right? Because that will be the critical speed, and the speed that you give should be just below that value, right? So if theta is 90 degrees, then in that case, this bob would have traveled up to this point, right? Now, to analyze this, once again, let's look at the forces which are acting. We know there's mg and there's tension, right? Now, we have repeatedly argued for such situations that work done by tension is 0. The reason being that tension acts perpendicular to the instantaneous direction of displacement, right? Well, now that we have learned power, we can give another argument, that is, which is a much stronger argument, that power delivered, the instantaneous power, is F dot V, right? Now, in circular motion, you see that the force is towards the center, which is the normal direction, right? And velocity is always tangential. Now, the normal direction is perpendicular to the tangential direction, so this dot product would be 0, which means the instantaneous power delivered is 0 at all instances of time, right? So if 0 power is delivered throughout the interval, the total energy delivered or the work done has to be 0, right? So therefore, we can tell that work done by tension will be 0. Now, for gravity, as we've been doing so far, we'll assume the Earth is part of our system, and rather than thinking about the work done by gravity, we'll talk about potential energy, right? So once again, we have circumstances where we can conserve mechanical energy. So what we can say is, whatever is the loss in potential energy should be the gain in kinetic energy, right? But in this case, it's actually quite the opposite. A better way to interpret would be that loss in kinetic energy is equal to gain in potential energy, because we see that the particle initially had some kinetic energy, and eventually in its final position, it only has potential energy, right? Now the reason for that is because we've taken the case that theta is 90. So we are talking about a case where this pendulum just manages to reach this position. Now when we are saying that it just manages to reach there, it means it just stops there and then comes back, right? So we can be sure that in this position, the speed of the bob was 0, right? So the loss in kinetic energy, it's simple to write, is equal to half into m into v naught square, because the final energy is 0. This should be equal to the gain in potential energy. Now once again, before we write potential energy, we need to set a reference, right? So for that, let's set our reference at the lowermost point, and at this point, let's say that the potential energy is 0. Right. Now, if that is the case, we are talking about a point mass which has basically risen to a height L, right? Once again, we need not concern ourselves with the horizontal displacement because potential energy changes only when there is vertical displacement. So in this case, the particle has gone up a height L, which is equal to the length of the string. So the gain in potential energy is simply mg into L, right? So this is the conservation of energy principle. We have seen that whatever energy is lost, whatever kinetic energy is lost, has to be gained in the form of potential energy, since there is no external agent doing any work. So this tells us that V naught is equal to under root of 2gl. So this is the speed, this V naught that we have found is basically the speed which, if given, this pendulum will just manage to reach this point and then come back, right? So for all values of V naught less than root 2gl, we can say that the oscillation will be such that the angular displacement will be less than 90 degrees. And so let's write it down that theta naught, so theta naught is the maximum displacement, theta naught will be less than 90 degrees, and for such a case, what we can definitely tell is that string will never slack, because we saw that the term mg cos theta will always be greater than 0, right? For any value of theta less than 90 degrees, cos theta is greater than 0. So this first term can never be 0. Hence, tension is always more than 0, which means the string always remains taut. So the string will never slack. So this is a case when your speed is less than root 2gl. So now what we can definitely tell is that if you give a speed greater than root 2gl, this pendulum will certainly enter the first quadrant, right? Now when it goes to the first quadrant, there are two things that could happen. The first one is that it rises to a certain height, the string goes slack and it falls towards its center. Now let's look at the situation in this animation. Now as this ball is pushed, it crosses the 90-degree mark. Now pay attention that the ball did not really stop, but it fell towards the center. So notice that the ball never stopped, right? What happened was that at one particular point, the ball started to fall inwards. The reason is that the component of gravity that acts towards the center is too strong. So it is more than the required centripetal, and hence the ball falls towards the center. So we'll prove this in equations just after this. Now the second possibility is that you've thrown the ball so fast that the string remains taut and it manages to complete a vertical circle. And this is exactly what we are trying to inquire into, the minimum speed that is needed for this pendulum to be able to complete a vertical circle. So with this illustration, one thing we've understood is that what stands in the way is the fact that if speed decreases, then the component of mg will pull the ball inwards, right? The ball still had energy even when it started falling inwards, so it could have continued the upward journey, but the weight pulled it inwards, right? So what we have to ensure in equations is that tension never becomes zero, right? Because if tension does not become zero, that means the string remains taut at all points, and in that case, it will certainly go in a circle.